In this presentation, we will talk about the electronic concept known as capacitance. A capacitor is an electronic component whose main characteristic is its capacitance, and it is said to store charge and store energy, electric energy. A simple version of a capacitor is what's known as a parallel plate capacitor, so we will adopt that image of a capacitor so that you can sort of visualize what's going on in a capacitor. And it has two conducting plates. So again, a conductor is something that conducts electricity easily. Electrons move around in it very readily. And then between these two plates is some insulating material. And in the context of a capacitor and capacitance, we will call that insulating material a dielectric. And so here's our picture of a parallel plate capacitor. In black, we have some lead, some wire leading up to the capacitor, and then we have the large black vertical line representing the conducting plate, the first conducting plate. And then there is the second conducting plate on the other side with a lead or wire coming out of it. And then in between, we have this dielectric. So there's a battery in the circuit that's not shown, and a battery pushes charges around. It has some voltage, some ability to push charges. So it has some arrangement of charges inside that have a high energy, and it wants to lower that energy by having the charges leave one side of the battery and come into the other. So a battery pushes around charges. So it pushes the charges out onto this lead shown on the left, and those charges end up on the first of the conducting plate. So the first conducting plate gets a charge on it. So it used to be neutral, but now it has a set of positive charges. We're going to take the convention that positive charges are what are moving around. So now we have positive charges accumulating on the first plate. And they accumulate there because the dielectric, being an insulator, does not let them through. On the other side of the plate, it was consisted of atoms, and those atoms had positive and negatives. It had protons and electrons, and so it had positive and negative charges. And the negative charges are attracted by the positive charges on the other side of the plate, and they will stay around as they're attracted to the positive sides on the first plate. And then the positives that used to make those negatives neutral, they're pushed away. So the positives on the first plate will attract the negatives on the second plate and push away the positives on the second plate. And what will happen is, as many positives came onto the first plate, will leave the second plate. And so we will get some current on both sides that is equal in amount. It's not the same charges, but it's the same amount of charge. So we had the battery pushing positive charges onto the first plate of the parallel plate capacitor, but we can't go on like this. Those positive charges that are accumulating on the first plate, well, they don't like each other. They like charges repel. And so though that the charge on the plate begins to push back against the battery so that we do not put more charges that repel each other, that don't like each other, onto that plate. So the battery is pushing charges onto the plate. The plate, once it gets charged, pushes back, and at some point there is a balance in the push from the battery and the push back from the positively charged plate on the capacitor, and then the current will stop and the capacitor will stop, what we say, charging. Now overall the capacitor has no charge. There are positives on one side and negatives on the other in equal in amount, so overall the capacitor has no charge. But we talk about charging a capacitor, meaning getting a charge on one side of it. So when we get a balance between the push from the battery and the push from the positive plate, the first plate of the capacitor, then the capacitor will stop, as we say, charging. And then this concept here, we're going to introduce the concept now of capacitance, and this is going to be a proportion between how much charge and how much voltage. So there's going to be sort of more charge will come onto the plate if there is a larger push from the battery, and the capacitor's ability to push back will be related to this concept of the capacitor's capacitance. So again, when we talk about the charge on a capacitor, we mean the charge on one of the plates, or the first plate. And so then the charge is going to be proportional to the voltage. The voltage is the battery's push, and so we will get a charge that is proportional to the push of the battery. If the battery pushes twice as hard, we will get twice as much charge. And then we need a proportionality constant to turn this into an equality rather than a proportion, and that proportionality constant is C, the capacitance. So we have our equation for a capacitor, Q equals V times C. So the charge is going to be equal to the voltage times this capacitance. And then we will also at times need to solve this equation for the voltage, and that will be V equals Q on C, of course. So the quantity capacitance suggests that there is a capacity to hold charge. The more capacitance, the more capacity to hold charge. So a bigger C will lead to a bigger Q. The unit for capacitance is the Farad, named after Michael Faraday, shown in the picture here. And a Farad turns out to be a rather sort of large industrial-sized capacitance, and so we will often be talking about millifarads, microfarads, nanofarads, picofarads, small amounts of farads. Again, the capacitance is the ability for the capacitor to hold charge in QVC. The bigger C, the bigger amount of charge will be allowed to be stored on the capacitor. So the first dependence is the easiest to understand, that the capacitance is proportional to the surface area of the plate. A bigger plate can hold more charges. Those positive charges will be able to get away from each other on a big plate, and so more will be able to be held. The capacitance is inversely proportional to the distance between the plates. On one plate we will have the positive charges, and on the other we will have the negative charges. And the charges will stop being put on the plate because like charges repel and don't like each other, but this will sort of be soothed by the negative charges being on the other plate. And so the nearer the other plate is, the more sort of balance or soothing that these negative charges will do to so the positive charges on the first plate don't like each other, but they like the negative charges on the opposite plate, and having those negative charges nearby sort of calm down the situation, allowing more charge to be on the first plate. And finally, there's a dependence on the material, the dielectric between the plates. The dielectric, like all matter, is made up of protons and electrons and so on, so it's overall neutral, but there are positive and negative charges in there. And then when you apply the positive charge to the one side of the capacitor, negative charges to the other, you might get some aligning of the positives and negatives within the dielectric material, and so you will get the negatives of the dielectric material sort of lining up on the surface near the positives, and the opposite on the other side, the positives of the dielectric lining up next to the negatives. And this gives it the overall effect of there's seeming to be less charge, so you can get more charge on there because the effect of the charge is less. And the ability for these the material to do that is known as its polarizability. These dependences of the capacitance, especially on the distance between the plates, allows them to play certain roles in computers. Let's take, for example, a capacitive keyboard. So if under a key you have two plates of a capacitor, and then the physical act of pressing a key changes the distance between those oppositely charged plates, then you are changing its capacitance, changing one of its electronic properties, and that therefore it is electronically detectable. So I'm taking a physical thing, a person pressing a key, and turning it into an electronic thing that will then sort of be detected by the computer, and so we can detect which key was pressed. Another place where a capacitor plays a role in a computer is DRAM, dynamic RAM. So we want to store a bit of information, a high or a low, and so a capacitor can be charged or discharged. It may have a charge on its plate or have no charge on its plate. And so we can take a capacitor and combine it with a transistor, and that will give it a sort of on-off, or being read or being written to aspect. And then so the combination of the transistor and the capacitor can create the ability to store a bit of information and give us a memory, something that holds on to a state in a computer. Another place one finds capacitors is in a power supply. The capacitors in a power supply are rather large, and that makes them dangerous. So it's always a good idea to sort of not open a power supply. In fact, it takes a sort of a special tool to open a power supply, so that it should not be tried by sort of an ordinary person who doesn't know what they're doing. Okay, so a number of things must happen to get the power that comes from the wall and to make it useful inside a computer. So the power that comes from the wall is a rather large voltage, and that voltage must be reduced. That is the job of a transformer. Then the voltage that comes from the wall was alternating current going up and down, positive and negative voltages, and it must be made positive only, and that is the job of a diode. And then when the diode gets done with the job, it is still going up and down. It's positive, but it's still going up and down, and then it must be smoothed into a nice direct current, smooth, consistent voltage, and that's the job of the capacitor in a power supply. As we had previously with resistors, where we had a concept of equivalent resistance, with capacitors we have a concept of equivalent capacitance, that we might have some combination of capacitors, and we might be able to consider them to be replaced by a single capacitor, which will have the same effect as the combination. And then in such a case, we will be said to have an equivalent capacitance. And so it will be that the voltage and charge, in the resistor it was the voltage and the current were the same, and in the capacitance it's going to be the voltage and the charge are the same. So the equivalent capacitance will draw out the same charge for the same applied voltage as what it is replacing. So let us first consider capacitors in parallel. Remember our definition of parallel: connected by a wire on one side and connected by a wire on the other side. So the two capacitors C1 and C2 shown in the diagram here are in parallel. Things in parallel experience the same voltage, and so the charge coming out of the battery will split at the junction, and some of the charge will go onto C1 and some of the charge will go onto C2, but the two capacitors will see the same voltage. So each individual capacitor obeys the QVC equation. Q1 equals VC1 and Q2 equals VC2, and for the equivalent capacitor, Q total is VC equivalent. Now the charge divides up. Some of the charge went on to Q1 and some of the charge went on to Q2. So the total charge is the sum of Q1 plus Q2. If we make the substitution, Q equals VC, so replace all those Q's by VC's. We have VC equivalent is equal to VC1 plus VC2. But we know that the two capacitors see the same voltage, and they see the same voltage as their equivalent, so all those V's are the same, and so then we can divide by it. This gives us the equation for capacitors in parallel, that the equivalent capacitance is equal to the sum of the capacitors. Next, we're going to talk about capacitors in series. And we're going to end up saying that capacitors in series have the same charge. Let's just talk about what we mean by the charge on a capacitor to begin with. Overall, a capacitor is neutral. The amount of positive charge on one side and the amount of negative charge on the other are sort of equal and opposite, so that overall it's neutral. But so when we say that we are charging a capacitor, we are talking about just one of the plates. Okay, so now we have these two capacitors in series, and we're connecting them to a battery. The battery pushes around charges. It pushes around positive charges to get to the top plate of C1. That ends up pushing away the same amount of positive charge that were on the bottom plate of C1, leaving behind sort of a corresponding amount of negative charges. And those positive charges that left the bottom plate of C1 end up on the upper plate of C2, and then the corresponding amount of positive charge leaves the bottom plate of C2 and then goes off and back to the battery. So between the two capacitors, the bottom plate of C1 and the upper plate of C2 was original neutral and always is going to remain neutral. So the positive amount, and again, when we talk about capacitors being charged, we talk about just the positive on one of the plates, and the positive on top of plate C1 and the charge on the upper plate of C2 are the same amount of charge. And so capacitors in series have the same charge. Now we are in series, so the voltage has some push, and there's some push on the C1 and some push on the C2, and then it's overall the push of the two individual capacitors adds up to the total push. So the voltage is going to be split, whereas the charge is going to be the same. Each individual capacitor obeys QVC. In this case, we're solving them for the voltage, so V equals Q over C for V1 and for V2, and also for the equivalent. Now the voltages add up. V1 plus V2 adds up to the total voltage, and then we can substitute in Q on C for each of the voltages. So the total charge over the equivalent capacitance is equal to Q1 on C1 plus Q2 over C2. Now we've argued that capacitors in series all have the same charge, and so all those Q's are equal, and then we can divide through by the Q, leaving just ones in those numerators. And so we end up with the equation for capacitors in series, which is 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2, a reciprocal addition. So let us consider the circuit with 3 capacitors and try to work it down to one equivalent capacitor. So first we notice that the 2.5 microfarad capacitor and the 1.5 microfarad capacitor are in parallel. There's a wire connecting the top plates and there's a wire connecting the bottom plates. That makes our definition of parallel. And capacitors in parallel add, so we will be adding 2.5 and 1.5 to get an equivalent capacitance of 4 microfarads. Now I just want to explain what this little resistor is in there hanging around for. We know that the voltage across a capacitor is given by the charge on the capacitor divided by the capacitance. And so we imagine that if initially when this circuit begins, if the two capacitors are uncharged, then there's no voltage across them. And then, but we must use up, as we go around a circuit, the 5 volts. And so that's the purpose of the 0.2 kilo ohm resistor here. So when we first start and there is no charge on the capacitors, something needs to use up to take the brunt of that 5 volts. So that's what the 0.2 kilo ohm is doing there. And then we've replaced, as we said before, the 2.5 and the 1.5 microfarad capacitors, which were in parallel, we replaced them with an equivalent capacitance of 4 microfarads. Now we are going to replace the 3.5 microfarad and 4.0 microfarad capacitors, which were in series, with their equivalent. And so we use that reciprocal addition form of 1 on C equivalent equals 1 on C1 plus 1 on C2, and that yields 1.87 microfarad. So we've replaced those two in series with this one equivalent one. And now we would like to use QVC rule to find we know V and we now know 1 capacitance, and so we can find Q. And we still have the 0.2 floating around, but the 0.2 kiloohm was for the beginning when the capacitors were uncharged. And what we imagine now is that it's a long time and the capacitor is charged, and therefore the current has stopped, and thus the resistor is doing nothing. The voltage across the resistor would be when there's a current, but if the current has stopped, there will be no resistance, and we can think of it as sort of all capacitance. Next, we can take a step backward. That 1.87 microfarad equivalent capacitance was 2 capacitors in series, a 3.5 and a 4. Now we know that capacitors in series have the same charge and the same charge as their equivalent. So we know the charge on both of these capacitors is 9.33 microcoulomb. And since then we know the charge and the capacitance, we can find the voltage. And so we find the voltage across the 3.5 microfarad capacitor is 2.67, and the voltage across the 4 microfarad capacitor is 2.33, and then we recognize that the two of those add up to the full 5 volts of the battery. We can make another backward step and say that that 4 microfarad capacitor was really a 1.5 and a 2.5 microfarad capacitor in parallel. Things in parallel have the same voltage and have the same voltage as their equivalent. So we know the voltage of these two capacitors is 2.33 volts. Now we know their capacitance and we know their voltage, so we can find their charge Q using QVC. So we take the voltage and multiply it by the capacitance, and we find that the charge for the 1.5 is 3.5 microcoulombs, and the charge for the 2.5 is 5.83 microcoulombs. And again, we recognize that if we add these two charges, we will get the sort of net charge out of the battery that was 9.33 microcoulomb. Now here we are testing the circuit in Multisim. We have no easy way to measure the charge on a capacitor, but we can measure the voltage across the capacitor with the voltmeter shown. Just want to point out two things about the circuit. The purpose of those switches was that when we are playing with the circuit, that we can close those switches. There will be an easy path from the top side of the capacitors to the bottom side of the capacitors, and this will discharge them. There will be an easy path from the positives on the top plate to get to the negatives on the bottom plate, and then the capacitor will discharge. When the switches are open, then the circuit will be charging the capacitors as desired in this circuit. But we have to be careful of the voltmeter. The purpose of a voltmeter is to measure a voltage, but not really to participate in the circuit in any way. But the voltmeter is a path for current to flow, and so it has a very high resistance, and we want to make it sort of extremely ideal to give it a very, very high resistance to make sure that only the most minimal amount of current goes through the voltmeter, and so that we are not discharging those capacitors, that they will get the charge that we are expecting them to get and read the voltages we are expecting them to read. So again, the purpose of a voltmeter is to observe and not participate, and the way we get that to happen is to give it a very, very large resistance.